is a Halogenoalkane tutorial presented by the USHLDB. We reference Cambridge International AS A-Level Chemistry by Laurie Ryan and Roger Norris. So, halogenoalkane, start with the learning outcome. You should be able to write equation reaction halogenoalkane when they undergo nucleophilic substitution, hydrolysis, formation of nitrile, formation of primary amine, and all that. So you have to describe and explain the SN1 nucleophilic substitution unimolecular and bimolecular mechanisms, and then interpret the different reactivities of halogenoalkane. Explain the uses of fluoroalkanes and fluorohalogenoalkane in terms of the relative lack of reactivity. Explain the concern about the effects of chlorofluoroalkane on ozone layer. So now let's visualize. So the introduction just says that halogenoalkanes are mostly very used in cases of anesthesia. As you can see where this child having anesthesia being placed, and they have highly volatile this anesthesia. So this is the introduction. So now let's go to the forms of the type of reaction that halogenoalkane mostly do. We have nucleophilic substitution reaction. As you can see here, you see a substitution reaction occurring between a halogenoalkane, in this case bromoethane, and sodium hydroxide. So between bromoethane and sodium hydroxide, you see that the sodium, there is going to be substitution of bromide ion and the hydroxide ion to produce this ethanol and sodium bromide. So this other form of equation can also be used, and this is a nucleophilic substitution. The question is why the word nucleophilic. So we need to first point the fact that let's define what is being said to be electrophilic and a nucleophile and an electrophile. A nucleophile is a species that is going to react with an electron. A nucleophile is going to react with an electron deficient center. So when we say nucleophile, we just say that you love nucleus, so you love positive ions. Since you love positive ions, you are going to react with an electron deficient center. So now electrophile is a species that is going to react with an electron rich center. So it loves electrons, so it's going to react with electron rich center. So phile, you need to know that philic just means loving in Latin. So now let's continue by saying seeing the reaction of the sodium hydroxide and bromoethane. This reaction occurs in case of heat and your reflux. So you see that you have a heat here, you have a reflux here with a condenser. Water is coming down and then water coming out. So as every time you are heating, you are cooling it. Every time you are heating, you are cooling it, such that all the reaction take place. You don't want to evaporate the halogenoalkane, so that's why you heat it and cool it. You heat it and cool it in a reflux. So you see that all of these are going to react to produce this molecule of ethanol. So now let's visualize the reaction preference. So you need to know that fluoroalkane are going to be less reactive compared to chloroalkane, which are compared to bromoalkane, and then iodoalkane is going to be most reactive. And the question is why. If you realize the bond energy between carbon and fluorine is going to be strongest, so you have 467 kilojoules per mole, and the bond energy is 346 for chlorine. For bromine is going to be 290, and for iodine is 228. So it has a weakest bond. So it implies that much more heat or much more energy is going to be used in order to break down the bond between carbon and fluorine compared to the bond between carbon and iodine. And the reason is just because fluorine is very small in size. Since fluorine is small in size, it can easily penetrate the electron sphere of carbon atoms. Since it can easily penetrate, it can now form a strong covalent bond with this carbon. So these are the points to note. So now the next part is going to be substitution with cyanide ion. So this is the next reaction that is going to occur. So in this case, you have substitution. You have seen the substitution with OH ion, hydroxide ion. Now in the cyanide ion, just substitute, and this position we have propanitride. So that's another thing. So the next one, you have substitution with ammonia. So just bind with ammonia. Ammonia has a lone pair of electrons. This lone pair of electrons can come on this side and cause a breakdown of bromine. So you have ethylamine that is going to be formed. So now we have mechanism of nucleophilic substitution. We need to know that there are two main types of mechanisms in nucleophilic substitution. We have nucleophilic substitution by molecular, which is represented with 2, and this 2 just means that what the rate of this reaction is going to be both controlled by the ion, that is by the both reagents which are being required in the reaction. That the rate of reaction is going to be proportional to the concentration of halogenoalkane and the molecule with which halogenoalkane is going to react with. So this is how to see it. So this is bimolecular. So in this case, you have OH reacting with this propane molecule. You have OH reacting with this bromoethane molecule. And now since you have the OH, you see that this is going to bind. As it binds, it's first going to form an intermediate molecule. That's why it's said to be bimolecular. So it's going to form an intermediate molecule, and then then you see that this bromine is going to come out and is going to form this. So this is the next molecule. So since there are two molecules, that's why it's called substitution molecular by nucleophilic substitution by molecular. So now, and the rate of reaction here is going to be rate is directly proportional to the concentration of the bromoethane and times the concentration of hydroxide ion, because it depends on both of these molecules. That's why it's written here SN2. So now let's visualize, and this SN2 only occur for what? Primary haloalkanes, and the reason is because the intermediate ion that is going to be formed is a primary carbocation, and primary carbocation are least stable. That is why you need an intermediate molecule that is supposed to be formed to replace that primary carbocation, and this is going to form this last molecule. So now let's visualize the mechanism of tertiary haloalkanes. For tertiary haloalkane and with also secondary haloalkane in presence of alcohol, because if you place secondary haloalkane in alcohol, they are going to act with the method of substitution nucleophilic unimolecular. But when you place the secondary haloalkanes in ether, they instead act as substitution nucleophilic bimolecular, that is by reacting as primary haloalkanes. So this is the case. So for tertiary haloalkanes, they are going to do substitution nucleophilic unimolecular, and this one here only means that the rate of reaction is only going to be directly proportional to the haloalkane which is being reacted. So let's see this example. So we have this tertiary haloalkane here. So in this reaction, the mechanism is going to be shown here. Bromine is going to come out first, then the hydroxide ion is going to. So this is a slow step of the reaction. Then the hydroxide ion is going to enter here, which is going to bind. So you see that what the rate of the reaction here, you know that normally the rate of reaction is controlled by the slow step. In this reaction, the slow step is this one, and in this reaction, the slow step is this one. Since the slow step is here, the reagent here is only haloalkane. That is why the rate of this reaction is only going to be depending on the tertiary haloalkane. Why? Since the slow step is this one, the rate of this reaction is going to depend on both the primary haloalkane and the hydroxide, and this is the first step of the reaction. So these are the points that you have to note. So now let's visualize. So this is tertiary halogenoalkane and all that. So this is the mechanism that have occurred. So now we have elimination reaction. So these are all the points. So now let's see elimination reaction. So halogenoalkane also undergo elimination reaction. So you need to know that the elimination reaction instead occur in cases of concentrated sodium hydroxide. When you use dilute sodium hydroxide, you instead have an addition, you have substitution reaction. But when you use a concentrated sodium hydroxide, you are going to have elimination reaction. So when you use concentrated sodium hydroxide, this is going to be eliminated in case of in the use of say-safe rule. So they are going to be eliminated in form of say-safe rule. So you need to know that when they are going to be eliminated, in order for the molecule to become much more stable, so say-safe rule stated what in an elimination reaction, the double bond is going to be formed in the intermediate portion of the molecule. It's going to be formed in the middle of the molecule. So that's say-safe rule. So that's it. So just the opposite of Markov-Nikov rule. So that's the point to note. So now, so this is used in all that. So now let's see the uses of halogenoalkane. Halogenoalkane are rarely found naturally, but they are important chemical industries. They are frequently made, intermediate, and all that. So we have already seen one function, the halotane. So that function of halotane was in cases of what we've seen that halotane was used as an anesthetic chemical. So the next thing, we can also have fluoropolymers, which can be used in the formation of plastics and all that. So we said to say thanks for your kind attention. Please don't forget to like and subscribe for our channel. Thank you.